Let us try to understand about a constraint called as set input delay. So you can see here the SDC command used to specify delays on input ports. So this is the SDC constraint called as set input delay, which is used to set a delay on the input ports, and this is the syntax of that particular command. So here you can see set input delay followed by these are switches. So hyphen clock, you have to give the clock name, followed by hyphen clock fall. This is about level sensitive, and hyphen rise fall max min followed by the hyphen delay, and this is used to mention the latency, that is which is network latency followed by the source latency. So please check the video on clock latency so that you will be understanding what is meant by source latency and network latency. And here by using delay value we will give the value followed by where we are applying, that is at port and pin list. And if you see the detailed explanation, you can see here hyphen clock is one of the switch followed by the clock name. So it specifies the clock associated with the input signal. And next hyphen clock fall. So here suppose if the clock is coming from some of the block which is present outside our block and it is triggered by the negative edge, then you can go for clock fall. So simply by default it will be positive edge trigger only, and suppose if it is negative edge trigger, then you have to use the switch called as hyphen clock fall. Next level sensitive, if the device which is present outside our block is not flip flop, suppose if it is latch, then you have to use this particular switch called as hyphen level sensitive. So it indicates the input is level sensitive instead of edge triggered. And next hyphen rise and hyphen fall, these are the two switches that specifies whether the delay is for the rising or the falling transition of the input. And max and min value, generally this min value is used for hold and max value is used for setup. So it indicates whether the delay is maximum or minimum arrival time. Next hyphen add delay, so it adds the specified delay to an existing delay for the port. Suppose if you are getting the data from multiple blocks and those blocks contain some of the flip-flops which are triggered by different clocks, then we have to use the switch called as hyphen delay. And if there is any network latency included, then you have to use this particular switch. So it includes the network or interconnect latency in the delay. Next hyphen source latency included, so it is used to specify the source latency. Next hyphen delay value, so we have to give the delay value like how much time it is taking for the data to be available at our port, followed by this is port and pin list. So it includes the list of input ports or pins to which delay applies. So we have to see each and every switch in detail. So let us try to understand that in the upcoming slide. Let us see about clock specification. So hyphen clock is a switch. The hyphen clock option in set input delay is used to specify the reference clock with respect to which delay value is defined. This should usually refer to the clock that triggers the signal arriving at the input port. So this is our block B1 and we want data to be available at this particular input port I1. So the data for this input port I1 is coming from some of the block which is present outside our block B1. So here if you see one flop is connected to combo, and from combo we are getting the data. But you can see here this flop is triggered by clock 1. So whenever the clock triggers, then only the data from D pin will be available at Q, and that Q pin will go through this combo which will have some amount of delay, then only the data will be available at our input port I1. So you can see here the reference event is clock 1. So we have to use the switch called as hyphen clock and give the name as CLK1. But you can see here this clock 1 is connected to both flip flop 1 followed by the flop or something which is present within our block 1. So that's why we are giving hyphen clock followed by this name. Suppose if this is not connected to both the flop and block B1, there is some other concept called as virtual clock. We will see that one in the upcoming slide. So you can see this particular figure, clock specifications for input delay. Let input I1 of block B1 be driven by flop F1. So this input I1 which is part of block B1 is driven by flop F1. This is something which is lying outside of B1, which lies outside B1, so possibly in another block or in the top level. Suppose the clock triggering F1 also enters block B1 and is named CLK1 in block B1. You can see here this is the triggering event which is connected to both flop F1 followed by some of the flop which is present in our block B1. In this case, the clock name should be specified as CLK1. So we know this is a name which is given to that particular clock. So we have to use this particular name only. So hyphen clock followed by this name. The input arrival time is measured with respect to this clock as a reference event. So here the CLK1 is our reference event. It does not matter what the same clock is called when driving F1. So it can be any name that is driving F1 or driving B1. So depending upon the name, we have to give the convention like hyphen clock followed by that particular clock name. Now this is another concept which is called as virtual clock scenario. If the clock triggering F1 does not enter B1, suppose if this clock is triggering only F1 and it is not entering B1, there is a concept called as virtual clock. A virtual clock must be declared for B1. Suppose if this particular clock is not present, then we have to declare it with respect to a concept called as virtual clock. This virtual clock must have the same characteristics as the original clock. The virtual clock can then be used as a clock name in set input delay. As here the same clock is connected to both flop 1 followed by some of the flop present in B1. By default we know like hyphen clock, this is the clock name. Suppose if this clock is not present, I mean if it is not connecting to block B1, then we have to use the concept called as virtual clock. Next, clock edge consideration. By default, the delay is measured with respect to positive edge of the clock. So by default, we know this is triggered by the positive edge. Suppose if there is anything called as negative edge, then we have to use a switch called as hyphen clock fall. So if F1 is triggered by negative edge, use hyphen clock fall as the option. This sets the reference event to the negative edge instead of positive edge. By default, it will be positive edge. Suppose if it is negative edge, then simply use this particular switch called as hyphen clock fall. So let us try to understand it by means of an example. So clock period is 10 nanosecond and waveform is 0 and 5. Here 0 is rising, 5 is falling. F1 is triggered by the falling edge. As it is falling edge, you have to use a switch called as hyphen clock fall. So the following commands are equivalent in timing analysis. So you can see here set input delay hyphen clock name. So this is the clock and the name given to it is CLK1. And suppose if it is negative edge, then use a switch called as hyphen clock fall, and this is the amount of delay which is 2 nanoseconds, and we are applying it to the get ports I1. Next, set input delay hyphen clock CLK1. This is the delay that it is taking to come to the input port I1, and we are applying it to the port I1. But here if you see here, we are not using any switch called as hyphen clock fall, so by default it will be positive edge triggered. So preferred, use the first command because it accurately reflects the actual triggering edge of F1. So depending upon our requirement, we have to see and we have to use this particular switch. If it is simply positive edge trigger, use the second command. If it is negative edge triggered, use the first command. I mean include the switch called as hyphen clock fall. Next, combinational path scenarios. If the input pin is part of combinational path only, there may be no clock triggering the signal. We have seen already this one. Here this combinational path is something which is getting data from this flop which is triggered by CLK1. But if you see this particular scenario, here this port I1 is getting data only after passing through some of the combo and there is no clock. So in this case hyphen clock is not required. So if you are writing constraint for this, hyphen clock switch is nowhere needed. Similarly, hyphen clock fall is also not needed. Why? Because if clock is only not there, then there is no point of taking either positive edge trigger or negative edge trigger. So that's what I mentioned it here. In this case, hyphen clock is not required and the reference event is considered as time 0. The hyphen clock fall option has no significance without a clock. Suppose if clock is not there, then there is no point of positive edge trigger or negative edge. Next, coming to the note, most modern designs are synchronous. So set input delay usually includes a clock. So as everything is synchronous nowadays, so there will be a concept of clock. Purely combinational parts can also be constrained using other constraints. So we'll see more detail about how to constrain this combinational part in our upcoming video. Now let us try to understand about the switch called as hyphen level sensitive. So till now we have understood the switch called as hyphen clock followed by hyphen clock fall. Now let's see level sensitive. As I already told you, if the block that is present outside our block is driven by latch instead of flop, then only we have to use this particular switch called as hyphen level sensitive. So see here, the hyphen level sensitive switch option should be specified if the launching device is a latch instead of flip flop. So here we are getting data from the flop. So that's why we are saying this is something either positive edge trigger or negative edge trigger. If it is negative edge trigger, we are using a switch called as hyphen clock fall. Suppose if it is positive edge trigger, we are not using any switch. Why? Because by default it will be positive edge trigger. Now suppose here instead of flip flop, if it is a latch, then you have to use this particular switch called as hyphen level sensitive. Coming to conceptual meaning, a latch can be transparent, meaning the signal can start propagating anytime the latch is open. So it can be either positive level sensitive latch or else negative level sensitive latch. If it is positive level sensitive latch, it will work whenever the enabled signal is high. If it is negative level sensitive, it will work whenever the signal is low. I mean level sensitive high means it is 1, level sensitive low means it is 0. Using this option allows timing analysis to borrow time from the current cycle, potentially reducing setup slack for downstream parts. And caution, this option must be used carefully because different tools handle it differently. Some tools or translators may ignore this option entirely. If the designer chooses to use it, they must ensure that all tools in the flow interpret it consistently to avoid incorrect timing analysis. Now let us try to understand about hyphen rise followed by hyphen fall switches. The hyphen rise and hyphen fall options are used to specify which signal transition the input delay corresponds to. So is it the delay corresponds to rise transition or fall transition? should be indicated by means of these two switches. Hyphen rise means the delay corresponds to the rising edge of the input signal. If it is hyphen fall, the delay corresponds to the falling edge of the input signal. And coming to the usage, these qualifiers are needed only if the input arrival times are different for rising and falling transitions at the same input port. If neither hyphen rise nor hyphen fall is specified, the given delay value is applied to both transitions. So if you are not using these two switches, then by default the same value will be applied to both rise transition as well as fall transition. And coming to the practical note, in CMOS, which is complementary metal oxide semiconductor circuit, path delays for rising and falling transitions are usually similar. So hyphen rise and hyphen fall are rarely used. So these two switches are rarely used. Now let us try to understand about min and max qualifiers. So this min will be used for hold and max will be used for setup. So see this one. The hyphen min and hyphen max options are used to indicate whether the specified input delay represents the earliest or the latest arrival times of the signal. So I have made a detailed video on what is meant by this earliest time and what is meant by latest time. So please check that video. If not, I will include that particular link in this video description. Now coming to hyphen min, it specifies the earliest arrival time for the signal. This value is used for hold time checks inside the current design. If it is hyphen max, it specifies the latest arrival time for the signal. This value is used for setup timing checks inside the current design. So simply remember this point. If it is min delay, it is used for hold analysis. If it is max delay, that value is used for setup analysis. So default behavior, if neither min or max is specified, the same delay value is applied for both setup as well as hold checks. Typically, designers specify only the hyphen max delay, which corresponds to the setup analysis, since setup constraints are usually more critical. Coming to the practical considerations, in modern nanometer technology, the hold time values for individual flops have become very small, often negative. Because of this, the data path delays. So data path delay is something like from the launching flop clock to queue delay plus interconnect delay is usually sufficient to satisfy hold requirements. Hence, hold checks are naturally met even without specifying a separate switch called as hyphen min. Suppose if it is needed, use a switch called as hyphen min for hold, and by default we have to give hyphen max if it is for setup analysis. However, if the input signal drives an element with a large hold requirement, the hyphen min delay must be specified accurately to ensure proper timing verification. Now let us try to understand about hyphen add delay. So generally this switch is used if you are getting data from multiple blocks which are having flops driven by different. So you can see here, when multiple reference events are there, then only we use this particular switch called as hyphen add delay. Most timing analysis tools provide an interactive shell that allows designer to modify or update previously specified timing constraints. By default, if an input delay is specified for a port, any new specification overrides the prior delay constraint on the same port. Suppose if you are missing or if you forgot to add this particular switch called as hyphen add delay, if we are getting data from the multiple blocks which are driven by the flops with different clocks, then one particular constraint will be overridden by the new constraint that you are applying. So it will be more clear when we see an example. So I'll show you the examples in the upcoming slides as well. So coming to this, however, when a designer wants to specify multiple input delay with respect to different reference clocks or events for the same input port, the hyphen delay option must be used for all subsequent specifics. So usage rule, for the first input delay specification on an port, hyphen add delay is not required. For additional specifications, hyphen add delay must be used. If hyphen add delay is mistakenly applied to the first specification, it is ignored by the tool. So these are some of the important usage rules that you need to remember. The presence of the add delay switch tells the tool that the new constraint is additional and should not override existing constraints. So meaning we are applying multiple constraints on the same port. In contrast, if this switch is not used, the new specification overrides all previous ones for that particular port. So let us try to understand the same concept by means of examples. So set input delay hyphen clock CLK1 and hyphen min, this is the value. This is the delay value which is 3 nanoseconds and we are applying to the port called as get port I1. It specifies the minimum input delay. So generally we know that this minimum input delay is used for hold analysis and maximum input delay is used for setup analysis. So for port I1 related to clock CLK1, at this point only hyphen min delay is set and no max delay is set. Coming to next one, set input delay with respect to clock CLK1 and max value is 4 nanoseconds. We are applying it to the same port which is input 1. Min is used for hold, max is used for setup. Remember this point, min for hold, max for setup. Now you define the maximum input delay. This is used for setup analysis for the same port I1 related to the clock CLK1. Since hyphen max was not previously defined, this is valid. Now both min and max values exist. So separately, if you want like this, you can mention. If not, I'll show you one more format. Set input delay hyphen clock CLK1 followed by the delay value is 3.5 and we are applying to the port input I1. So here you can see I'm not using any switch called as hyphen min or hyphen max. So by default, this 3.5 nanoseconds will be applied for both min and max. This is a shorthand command without min and max, which means it overrides both the previous delays hyphen min and hyphen max for clock CLK1 on port I1. After this, the only effective delay for the clock CLK1 is 3.5 nanoseconds for both setup as well as hold. So this is the beauty of writing SDC constraints. One more, set input delay hyphen clock. Here this is another clock which is CLK2 and hyphen add delay 3 nanoseconds is the delay and I'm applying it for input port. You can see here already there is a constraint present on the input port of 3.5 nanoseconds with respect to clock CLK1. Again we are getting data from some other flop which is present outside our block and that is driven by clock CLK2. So that's why here I'm giving the clock CLK2 followed by I'm writing hyphen add delay. Why? Because on this input port only IN1 I am adding one more delay which is 3 nanoseconds, that is with respect to CLK2. So that's why we need to add this particular switch called as hyphen add delay. So this adds an additional input delay constraint for another clock CLK2 without removing the previous clock CLK1. Because of hyphen add delay, input IN1 now has two timing relationships. One is with respect to CLK1 which is having a delay of 3.5 nanoseconds and another is with respect to CLK2 which is having a delay of 3.0 nanoseconds. Suppose if you are not adding this particular switch, then simply it overwrites that particular previous value. Set input delay hyphen clock CLK3. This is with respect to clock 3. This is the value. Now I am applying on input port IN2. IN2 had no prior input delays defined, so this new constraint is valid and it is independent. So here there is no effect. Why? Because we are applying it to the different port IN2 and that is with respect to clock CLK3. So this is the final summary. Input delay with respect to clock CLK1, min value is 3, max value is 4. I am applying on the input port IN1. Suppose if you are adding this third constraint, I mean the third line of command, then simply it overrides this min and max value and simply it will go with the value called as 3.5. Next, coming to the fourth one, set input delay with respect to clock CLK2 and I'm applying it on the same input port. Now it is with respect to CLK2. So that's why I'm adding a switch called as hyphen add delay. And this is something which is purely independent of above constraint that we have written. So there is no effect of this. So coming to the final summary table, input port IN1 with respect to clock CLK1 both replaced 3.5 nanoseconds. Means this 3 and 4 are simply replaced with this 3.5 nanoseconds. Next, port IN1 with respect to clock CLK2 added with hyphen add delay. So on the input port IN1 only I am adding a delay of 3 nanoseconds, that is with respect to CLK2. So that's why I am adding a switch called as hyphen add delay. Next, on input port IN2 with respect to CLK3, this is a fresh constraint. So it is independent of all the above constraints that we have mentioned. So this is the important tip that you need to remember. Always use hyphen add delay when a single input can be launched by multiple clocks. Otherwise the tool will override the previous constraints. If you are not adding this particular constraint switch, then simply it will override the previous constraints that you have defined. Now let us try to understand about the clock latency switches that are present in this set input delay. So in the previous lectures, we learned that clock experiences some delay along its path before the actual trigger reaches the flip-flop. So we have understood this concept and I've made videos on this clock latency also. There are two types of latency, that is source latency and the network latency. So that's what I've mentioned here again. Source latency means it is a delay from the clock source to the clock definition point, whereas network latency means from the clock definition point to the clock pin of the flop. This is the network latency. So typically input delay values are specified with respect to the clock reaching the launching flop. So it will be more clear if you see some of the examples. So you can see this example, consider the circuit shown in the figure. So here clock latency impact on the input delay. The delay value D1 is specified from F1 clock terminal to the I1 input pin of the block B1. So you can see here, whenever this particular clock triggers, it will have some of the delay called as clock to Q delay, and data will be available from D to this Q pin, and that data will go through this combo. It will have some amount of delay and again it will come to the input port I1. So here this delay I am considering as delay D1. The timing analysis tool calculates the clock arrival time at F1 based on the latency, but you can see here this clock is not getting triggered immediately. It is having some amount of delay. It is having a delay of L2 followed by the delay of L1. So this is our block, this is the blocks which are present outside our block B1, and we are getting the clock from the clock source. Here you can take this clock source as PLL or an oscillator. So as I told you, the delay from the clock source to the clock definition point. Here this is clock definition point. This is having a delay of L1. So this L1 is called as source latency. And from this clock definition point to the clock pin of the flop, it is called as network latency. So L2 is called as network latency. So that's what I mentioned here. L1 is source latency, L2 is network latency. So total arrival time is something which is summation of L1 plus L2. So after a delay of L1 plus L2, here clock gets triggered, then only the data from D goes to Q, and the Q value goes through combo, and then it will be available at I1. It then assumes the signal reaches I1 after an additional delay value of D1 as given by the set input delay command. So this is one of the example to understand the latency of L1 followed by L2. L1 is source latency, L2 is network latency. So including latencies in delay specification, if the designer has already included the source latency L1 or network latency L2 in the specified delay values, the corresponding switches must be used. So these are the two switches which are present in our particular syntax of set input delay. So this is a scenario when we have to use this particular switches, hyphen source latency included and hyphen network latency included. So hyphen source latency is included to mention source latency, which is L1, network latency is for L2. Depending on which latency are included, the designers can specify none, either, or both the switches. When these switches are used, the STA tool does not add the corresponding latency again. This effectively advances the launch clock edge since the latency is already accounted for in the delay value. So coming to the practical and recommended approach, these switches are rarely used. Generally, in the real-time scenarios, we won't be using this particular switches called as hyphen source latency included and hyphen network latency included. So these switches are rarely used in the real world design flow due to the following reasons. Tool inconsistency. Different EDA tools treat these switches differently. Some may even ignore them. If you plan to use these switches, you must ensure consistent behavior across all tools in your flow. Next, asymmetric behavior between the launch and the capture parts. Both the launching device, which is outside the block, and the capturing device inside our block usually experiences similar clock latency. The STA tool already considers latency inside the current block. Applying these switches changes the treatment only on the launch side, which becomes non-intuitive. Coming to the clarity and reuse of the constraints, it's conceptually simpler to define delay from the launching device to the input pin without considering clock source details. Also, when latency changes, you won't need to re-edit input delay constraints, making the constraints more reusable. So as I told you, in summary, the use of hyphen source latency included and network latency included is optional and should be avoided unless necessary. It is usually clearer and safer to exclude these latencies from set input delay specification. And let us see about the complete picture of input delay constraint. After understanding all the optional switches and qualifiers of set input delay command, the final step is to complete the input delay constraints by specifying the actual port or pin on which the delay needs to be applied, the delay value to be associated with those ports and pins. So these are the two important switches. Generally, if there is any clock, we have to use hyphen clock followed by the clock name and the delay value and where we are applying it exactly, at which port or pin that we are applying is what we need to mention. And sometimes hyphen clock followed by clock name is also optional. Suppose if you are not sure about what clock is triggering the block which is present outside our block, I told you there will be a concept called as virtual clock. We need to go with that, and that is also optional sometimes. So majorly we need to focus on two things, that is the delay value followed by the port at which that we are applying. All other options like hyphen clock, min, max, rise, fall, hyphen add, delay, etc. are optional and used only to refine or customize the constraint for specifying design requirements. So coming to the final summary, to complete an input delay constraint, you must specify the delay value. Like we need to specify the amount of delay value that it is taking for the data to be available from the outside world block which is present outside our block to the input port of our block. So the delay value is mandatory. It represents the arrival time of the signal at the input port followed by the port or pin, that is the point where we are applying that delay, the signal entry point where this delay applies. So this is the syntax of set input delay followed by the delay value and get ports port list. So these are the primary things that should be present, and hyphen clock is sometimes necessary and sometimes it is not necessary, followed by hyphen min max, like the min is used for hold and max is used for setup, and hyphen rise and hyphen fall are also optional. Similarly, hyphen add delay as well. So everything else such as clock association, rise, fall, qualifiers or latency consideration enhances accuracy, but it is not mandatory for basic input delay. So only delay value followed by where you are applying is important. So in this video we have understood about the constraint called as set input delay, followed by we have gone through in detail about all the switches that are present for set input delay.